So now that we have our distribution, we need to come up with a way to turn this into a confidence interval for the standard deviation sigma. Now, remember that it's the population standard deviation we need an estimate for, not the sample standard deviation. So if we start with the same assumptions we used to derive the distribution, that is, the underlying population is normally distributed with a mean of mu and a standard deviation of sigma, then 1 minus alpha times 100% of the values lie between those two critical values that we saw how to find in the last lecture. Right? That's what this inequality is saying. 1 minus alpha of the standard deviations in our population will satisfy this inequality. And remember, n and sigma are both constants. N is the sample size. I know how many items I sampled. And sigma is the population standard deviation. I may not know what it is, but it does exist. It's a number, right? It's a constant value. So what I want to do now is solve this for sigma squared. Right, so let's say I'm going to divide both sides by n minus 1 s squared. So this becomes chi squared L over n minus 1 s squared is less than 1 over sigma squared is less than chi squared R over n minus 1 s squared. And that's fine. I don't need to worry about the direction of the inequality. N minus 1 is positive, s squared is positive. Right, so I know I didn't just divide by a negative number. So now I'm gonna flip all three parts over. Right, that's gonna make the 1 over sigma squared into sigma squared, which is what I wanted. And doing that is gonna mean I have to change the direction of the inequalities. So this will become n minus 1 s squared over chi squared L is greater than sigma squared is greater than n minus 1 s squared over chi square R. And that's it. We're almost there. It's a little weird to write it this way. We usually do these things in ascending order, right, with the smallest item first. So I am going to flip this around and make this n minus 1 s squared over chi squared R is less than sigma squared is less than n minus 1 s squared over chi squared L. And that's my formula. Right? That's the formula that we're going to use to calculate the upper and lower bounds of our confidence intervals. In this case, just to be clear, we have got sigma squared in there, right? So this is sigma squared isn't the standard deviation, it's the variance. So what I have here is a confidence level for the variance of the population. Right, so now we have formulas that we need, right, for the lower bound and the upper bound, and there are a couple of important things to keep in mind. Right, first, notice that the R and L values are reversed, which we saw in the previous calculations. The lower limit is based on the right hand or the upper or bigger critical value, and the upper limit is based on the left hand or the lower critical value. So just keep that in mind, right? If you're ever trying to do this from memory, remember they get a little reversed. And second, unlike the formulas for the population means and proportions that we've seen, these are the actual upper and lower limits, not the margin of error. There's no need to add or subtract them from anything to get the final answer, all right? They are the final answer. All right, so let's look at an example. Right, I've got just a very mechanical one here. I want to find a 99% confidence interval for the variance of a sample with 21 elements and a sample standard deviation of 0.411. All right, well, think this through. All right, what are we asked to find? I was asked to find a confidence interval for the variance. Okay, so I read that, and the first thing I think is, okay, awesome. I have a formula for the lower and upper bounds of a confidence interval for the variance. It's these two formulas that I have right here on the bottom right-hand side. Right. So now I'm thinking, okay, what do I need to know to use these formulas? Well, I need to know the sample size, and that's good, right? I know that. N is 21, which tells me that my degrees of freedom is 1 less than that, or 20, right? I need to know the sample standard deviation, which is good. I've got that right here, right? Good progress, right? And I need to know these two chi-squared values, the lower and upper bounds. Okay, so let's see how we can do those, right? We know how to do this, but I still, especially when we're just getting started, I like to do a little sketch, draw a picture, right? So I'm going to have my lower bound chi-squared L, and I'm going to have my right hand or upper bound chi-squared R. And I know I want 99% in the middle. All right, that means alpha is 1 minus 0.99 or 0.01. And I need half of that over here. Well, half of that is 0.005. All right, great. So I'm going to my table here, right? I have 20 degrees of freedom. So I'm working this middle row. And the critical value that gives me 0.005 area to the right is going to come from this column. So there's, whoops, sorry, I went too far down, didn't I? Sorry, middle row, 39.997. Okay, so how about the lower limit? Well, I know I need 0.99 in here and another 0.005 over here. If I add those together, the total area to the right of my chi-squared L value needs to be 0.995. That is this column. So that gives me a lower critical value of 7.434. And now it's just arithmetic. Right now it's just arithmetic. Put these numbers into our formula. N minus 1 is 20 times 0.0411 squared. And here you need to be careful. Be sure you grab the right one. I need the right-hand value. That's 39.997. Right, not squared. Please remember that 2 in that chi-squared is not an exponent. Don't try to square things. Don't try to take a square root. It's just 39.997, almost 40. Then for the upper bound, it's almost the same thing. 20 times 0.0411 squared over the lower bound, 7.434. Now, go to your calculators. Right, you go to calculators, you get 0.000845. And you get over here 0.00455. And what goes in the middle? Right? What goes in the middle? Remember, if you think back to the previous discussions, this is S, excuse me, not S, it's the population. Sigma squared. That is a 99% confidence interval for the variance of this population. Now, if you're like me, I'll be honest. The first time I did this and I worked these numbers out, I looked at it and said, "Whoa, wait a minute, something went wrong." My number here, 0.0411, is not in that interval. Right? It should be in that interval. And then I realized, okay, stop. That's the standard deviation. And I have a confidence interval here for the variance. Well, if the standard deviation is 0.0411, then the variance is S squared, which is 0.00169, and that number is in my confidence interval, right? Which it should be, right? That's what we expect to happen. All right. How about this one now? Now, if you read through that, you'll see that this is almost, right, almost identical to the last one. All right, the only thing I changed here is I changed it from saying a confidence interval for the variance to a confidence interval for the standard deviation. Right? I just made one little change. So how can we do that? Right? How can we do that? Well, think about what we came up with on the last slide. Right? What was the last thing I wrote over there? 0.000845 is less than sigma squared. It's less than 0.00455. And I said, okay, well, that's nice, but I don't want to talk about the variance. I want to talk about sigma, the standard deviation. Well, getting there couldn't be easier. Just take the square root. Right? Take the square root of all three parts. You can do that. That's a fair operation. Right? If you do that, we get 0.029063 is less than sigma is less than 0.067414. Right? And again, you do a quick reality check. Yes, 0.0411 is between those two numbers. So if you want to, so let's take a step back. Right? If you want to find a confidence interval for the standard deviation, what you do is you find a confidence interval for the variance, and then just take the square root, right? And there's your answer. So I've got a somewhat more practical example here, right? You can pause if you need to, right? Take a second, read this over. So what we have here is a situation where we're building parts for a space vehicle, and some of those parts have extremely low tolerances. They need to have very exact dimensions, and in this case, we're doing that by looking at the weight. The weight has to be, excuse me, the maximum allowable variation is this very small number. Right, so using a 95% confidence interval, do we expect the manufacturing process to meet this standard? Well, in other words, I need to have some idea of what the population's standard deviation is. Well, I can't get it exactly based just off of an example, but I can create a confidence interval, right, which will give me, with some degree of confidence, an idea of where I can expect that value to be. Right, so we kind of know how to do this, right? We've got our formulas for the lower and upper bounds. It's reasonable to expect the weights are going to be normally distributed. Right, so let's see if we can pull some information out here. Our formula requires three things. The sample size, which we know, right? If you count them up here, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 values in my sample. And we need the two upper and lower chi-square values, which we now know how to get. And we need the sample standard deviation. All right, so I've got, obviously we're a little short on space, so I'll just pop this in here. A 95% interval means that 5% will be outside the interval. Half of 5% is 2.5%. So 2.5% has to be above the upper limit, that's 0.025. And 95% plus 2.5, that's 97.5%. That much has to be above the lower limit, right? And since we have 8 values here, the degrees of freedom is 7, and that gives me my 2 critical values, 1.69 and 16.03. So chi squared lower will be 1.69. Is that a 9? Yes. And chi squared upper will be 16.013. Right, now let me, since we aren't going to need the table again, right, so let's clear that out. And we can do our calculations. Right, oh no, sorry, wait, we need the standard deviation. Okay, it's not the most pleasant formula in the world, but we know how to calculate this. We have these data values. You can use the formula. There's only 8 of them. I type them into Excel. right? And according to Excel, the sample standard deviation is 0.001909. Okay, now we can go to our formula, right? I'm just going to put numbers in. N minus 1 is 7. 0.001909 squared over the right-hand value. See, I put U for upper, the R for right. So this is over 16.013 less than sigma squared, less than the numerator stays the same. The denominator changes to 1.69. Right, so these come out to some pretty small numbers, which is good, right? This is 1.59 times 10 to the negative 6th, less than sigma squared, less than 1.509 times 10 to the negative 5th. And, okay, so that's a variance, right? But I don't want the variance, I want the standard deviation. So just take the square root of all three sides. If you do that, you get 0.00126 less than sigma less than 0.00388. Okay. So there's my range. I am 95% confident that the population standard deviation is in there somewhere. So what's the answer to the question? Do you expect this manufacturing process will meet the standard? Well, I have to go with no. Excuse me. If you graph these, right, I think it helps to visualize, right? I have 0.00126 here, and I have 0.00388 here, and 0.0001 is here. 0.001. I don't know what the population standard deviation is, but I am 95% confident that it is going to be greater than that tolerance amount that we were given. Right? So I have to go with no. Our process is not meeting that requirement. Okay, so let me just hypothetically throw something out here. Let's say it had actually been like this. Let's say our lower bound had been 0.0008 instead. All right, then this is what the situation would look like. All right, so what would I have said in this case? How would I have answered the question? I would still have said no. I still would have said the process is not doing what we need it to do. It's possible that we are doing better than the requirement, but it's also possible that we're doing worse. Right? It's also possible that we're doing worse. And this is, and anyone from my generation who remembers the situation with the Challenger space shuttle that exploded after launch, you don't want to be uncertain here, right? This is not something where even if it had been more like this, right? I still would have said no. I would not want my name to be on the paper signing off on it. I would want to see something like this. I would have wanted my tolerance level to be up here and my confidence level to be down here. That scenario I would have been comfortable with, right? That one I would sign off on and say, yeah, our process is doing what it needs to do. Okay, so what's next? This is the end of our discussion of confidence intervals. And so we're moving into our final chapter. in our discussion of introductory statistics. And in this next lecture, we're going to talk about something called hypothesis tests, right? And the driving idea here is I know what I think the value of a population is. Kind of just take a very basic example. Conventional wisdom says the average human body temperature is 98.6 degrees. Okay? I go out and I take the temperatures of 20 healthy people and I get 99.1. That's higher. Right? I get an average of 99.1. Well, that's making me think maybe 99.6 isn't really it. Right? This is what a hypothesis test does. It lets me test to see what happened. Why was my mean different than what I expected? Was it the result of just normal random variation in the population? Or was there something else going on? Was there some problem with the initial 98.6 value? Right? So those are hypothesis tests. That'll be the last chapter in our discussion here.